Okay, this is the second part of chapter 11. So today we're going to continue on with our intermolecular forces. And so we should know all four types of forces. We should be able to tell which one should be our strongest one, right? So we have dispersion or our London forces. We have dipole-dipole, which is for our polar molecules. Hydrogen bonds, which is like a dipole-dipole, but it's a subset of it. It only happens when you have a hydrogen connected to fluorine, oxygen, or nitrogen. And then we have our ion dipole. So for all of those, our ion dipole is our strongest intermolecular force. And then within that, our hydrogen bonds would be our next one, right? London forces is going to be our weaker one. And so this is us putting that in action. So we're comparing things here. We're comparing things like water versus H2S. We're comparing things like our group 6A, and we're saying, well, if all of our hydrogens stay the same, why does our boiling point go up as we go from carbon to silicon to germanium and tin? And then why is group 4A always higher than our group 6? So there's a lot of different things there that you have to keep in mind when you're comparing them. And so you want to think about what the big component is. And so sometimes it helps to draw out your Lewis structures or your 3D structures. So if we're looking for water, why is water higher than H2S? Well, water, Lewis structure looks like this. Two lone pairs on the oxygen. Each hydrogen is connected to that oxygen. And so if we would think about this, this molecular shape is going to be bent, which means it is definitely polar. So it has London forces. It's got dipole-dipole. And then this one also has hydrogen bonding, because that hydrogen is directly connected to one of those three exceptions, or not those three exceptions, to one of those three elements. And those three elements are nitrogen, oxygen, fluorine. Now, our second part is H2S. So if we were to look at H2S, well, what kind of Lewis structure does H2S have? H2S looks very similar to lone pairs on that sulfur. So we're also bent. We also have a dipole moment, but we don't have any hydrogen bonds. So there's no hydrogen bonds. So if we want to really think about why water is such a higher boiling point than H2S, it has to deal with the hydrogen bonds that are present inside of water. Those hydrogen bonds are very strong intermolecular forces. Strong intermolecular forces, so that should be an F, leads to high boiling points, high melting points. Weaker intermolecular forces leads to lower boiling points, lower melting points. So now let's look at group 6A. Group 6A, we're looking at our carbon compared to our silicon, germanium, and tin. And all of those have this basic Lewis structure. We have the element in the middle connected to 4 hydrogens. They're all tetrahedral. And because those hydrogens are evenly spread out, we really are going to be nonpolar molecules. So if the molecules are nonpolar, then our only option for why they would change is their molar mass. So as our molar mass increases, our London forces also increase. And as our London forces increase, then our intermolecular forces are increasing and our boiling point is increasing. So that should be our trend from our carbon to our tin, is that as our molar mass is going up, so are all of our London forces. The last one, I'm going to erase the other parts so we can kind of see this a little bit clearer, is group 4A. So why is group 4A higher than group 6A? And so when we drew group 4A, we had decided that they were going to be bent for their shape. And not only were they going to be bent, they were going to be polar. On the other hand, for group 6A, those were all going to be tetrahedral. And they were all going to be nonpolar because those bond dipoles would be canceled out. And so when we compare why group 4A has a higher boiling point than group 6A, it comes down to the fact that Group 4A, all of their structures are polar, and so they all have dipole-dipole forces. And so that's what's leading to that. And so there's your explanation there. And so you want to make sure that you can predict what's going on for your different molecules. We should be able to anticipate who has stronger or weaker boiling points, melting points, or stronger and weaker intermolecular forces. We should also be able to identify all of the intermolecular forces present. So if we wanted to talk about water, water has London forces, it's got dipole-dipole forces, and it has hydrogen bonds. Something like CH4 only has London forces. And so then we should be able to understand how that relates to the boiling points as well. Today, what we're going to focus on is we're going to focus on our solids. Now, as we talk about our intermolecular forces, we should have an understanding of our phase diagrams. Remember that our phase diagram, the lower temperature and the higher pressure leads us to be in our solid phase most often. The middle section is going to be our liquid, and the high temperature, high or low pressure is where our gas should be found. So we just want to remember this in terms of our forces, so we can talk about things with higher intermolecular forces from their phase diagrams. Because if we look at our diagram, we know that at 1 atmosphere, our uranium F is transitioning from being a solid directly into a gas. So it's going to sublime. We could also compare this against another compound. And so if this one sublimes, and let's say that this temperature was 100 degrees Fahrenheit, if our other material sublimed at 80 degrees Fahrenheit, we should know something about their intermolecular forces. So if they're going through that same transition, the lower the temperature, the weaker the intermolecular force for that same transition. So our UF6 that sublimed at 100 degrees Fahrenheit is going to be less than, is going to be stronger intermolecular forces than our compound that sublimed at 80 degrees Fahrenheit. And so we want to make sure that we can understand that and tie that back into our phase diagrams. So the higher the normal boiling point of the liquid, the stronger the intermolecular forces. And so boiling point is an example of this. It can be any of those phase changes. If you want to do a brush up, we should be able to identify each of those points. You don't have to worry about D. We're not going to worry about the supercritical states. But all of those other parts, we should know. We should know what we would call those transitions and what states they would be. So in this case, this would be our solid, our gas, our liquid. This is going to be a gas going to a liquid, or a liquid going to a gas. So this is going to be vaporization or condensation. So we'd have both states present. This is a solid going to a liquid, or a liquid going to solid. So this could be melting, fusion. And then this one is going to be our triple point. So you want to make sure that you practice those and you remember what they are. Now, one thing that we haven't talked about is vaporization. And so vaporization is an important concept. We've talked about it a little bit in terms of vapor pressure, but now we're going to get into the why it makes a vapor. If we think about it, water has a boiling point of 100 degrees Celsius. And so we wouldn't anticipate that there will be much water in the air, because at normal temperatures, let's say it's 75 degrees out, 75 is way less than the boiling point of water. And so we should see it as a liquid. But vaporization happens because there's high energy molecules at the surface. And sometimes those high energy molecules, they have enough energy to overcome the attractive forces. Because they're at the surface, they can escape because there's not quite as many forces pulling down on them. This one here in the middle feels way more intermolecular forces than one at the top or one at the edge. Because that edge is going to have it interact not with the water molecules, but with some of the walls of the container, and it might not be as attracted to those. On the other hand, by itself or at the surface, it can have an open space above it where there's even less intermolecular forces. Now, what that means is that the larger the surface area, we generally see a faster rate of evaporation. It means that we have more molecules that are at the edge. So if we have something that's long and narrow, so not much surface area that's open to the air, you have a very slow evaporation rate. If you want something to evaporate quickly, spread it out, and then it evaporates. It's the same thing as if you've ever taken a shower. If you take a shower and you dry yourself off with a towel, if you ball that towel up into the corner, it's not going to be dry the next time you need it. But if you hang it and you spread it out, you create more surface area for the water to evaporate. So this vaporization is going to allow the liquid to escape and become a vapor because it can interact with the air. So remember that in our collection or our temperature, our molecules don't all have the same amount of energy. Their average energy is related to the temperature, but you have some that are fast and you have some that are slow. So this is our average right there. So we will have some, even at this lower temperature, where they can break away and turn into their gas, where they can escape from the surface. Now, the higher the temperature, the faster that rate of evaporation is going to be. So if we increase the temperature, if you've done this in a pot, you'll notice that your pot will start to get some water vapor at the top before it starts to boil. And that's because more and more of that vapor from that solution is turning in, or more and more of that water from your pot is starting to turn into vapor, and then it's condensing on your lid. Eventually, once you get to a boiling point, then it's going to transition at a much faster rate. So what this means is that the weaker the attractive forces, the faster this rate of evaporation is going to be. Instead of this line being so far, if we're a weaker intermolecular force, we don't need quite as much energy to separate. So the lower that line is, you can see how much more of those water molecules would have enough energy to escape. So this is how we kind of come up with the term volatile or non-volatile. So things that are volatile turn into vapor very easily. And that could be something like fingernail polish remover, so like acetone or gasoline. Both of those have low intermolecular forces, which is why you can smell them, right? When you open that container, it turns into a vapor. A lot of those liquids with those weak intermolecular forces are transitioning to be gases, and so you can smell them more easily. Other ones that are non-volatile ones, things like motor oil, they have strong intermolecular forces. Those strong intermolecular forces means that not much of it will turn into a gas, which makes them less volatile or non-volatile. So remember that vaporization, this transition from going from a liquid to a gas, this is going to involve that energy, right? So when high energy molecules are lost from the liquid, it's going to lower overall the kinetic energy of that liquid. If we went back to this, if we removed all of this section here from our liquid, we would be losing energy from that liquid. All the fast stuff has gone away. And so if we don't draw more energy back in, then temperature is going to decrease. And so vaporization is an endothermic process. On the other side, condensation is an exothermic process. So when something freezes, sorry, not freezes, when something goes from being a gas to a liquid, it's actually going to release energy. Now, you might know vaporization as being an endothermic process if you've ever sweated. When you sweat, your body is allowing that water to get to the surface where it can then vaporize, it can evaporate away. And as it evaporates, then we lose that energy and we start to we feel that endothermic reaction. And so then it tries to gather in energy to replace it, and that's where you start to feeling that cooling impact. And so that's how your body sweating ends up trying to cool you down, is because vaporization is an endothermic process. You can also imagine that for something to go from being a liquid to a gas, it requires us to input energy to overcome those attractions. So vaporization's an input of energy. So a delta H vaporization is always going to be positive because it's always taking it in, and then the delta H of our condensation is the opposite of that. And so it's going to be the negative side of things. So if we wanted to summarize that, which one of these is doing the addition of energy, that should be our vaporization. And so that's how you get our heating curves that look like this again. Is this section, this is tied in with that vaporization. Sorry. This one is our tied in of our vaporization. This one is going to be our fusion or our melting. Both of them are similar concepts, just different state transitions. Now, the reason why this is an important part is we can use it to separate out materials. And so distillation is one way that it can be used. So when we distill things, what we do is we slowly heat a mixture. In this case, this could be water and ethanol. As long as the two compounds have different boiling points, we're going to be able to separate those solutions from one another. So ethanol has lower intermolecular forces, and so it has a lower boiling point than water. So as we start to heat our compound or our solution, the ethanol is going to be the one to transition first to being a gas. More and more of that ethanol is going to vaporize. Now, there could be some water molecules that have enough energy to escape, but it's going to be a lot smaller fraction of it compared to the amount of ethanol. Now, as that happens, those ethanol molecules move up, and we're going to start to take that gas, and then we're going to put them in through what we call a condenser. So this condenser lowers that temperature, and it helps transition that ethanol from being a gas back to being a liquid. Once it turns back into a liquid, then it can be collected in this container here. Now, you might have heard things about being double distilled or triple distilled. All that means is that they do this process several times. And so each time you distill, you're going to make a more pure and purer liquid. The first time, if you do it very quickly, or if you have compounds that have similar boiling points, you still get some water that transitions over. As you do it more times, then we're going to be able to get larger and larger fractions of the ethanol to come out and less of the water to transition. So we're heating it here. It's going up into the apparatus. So we're turning that ethanol into its vapor. That vapor is getting cooled down by our condenser. And then we're separating the ethanol from the water. And so that's one way for us to use the intermolecular forces to help separate things. Once we're done with removing all the ethanol, so you'll notice this because our temperatures start to increase, but we won't see any more liquid coming out, then we can continue to heat it. We'll then be able to transition all the water, and then we'll be able to separate the water out. And so you can do this many different times. And so that's how we can remove many different compounds from a mixture. And so this distillation process is really common in the oil industry, as they take crude oil and they try to separate out all of the different types of hydrocarbons inside. Now, chromatography works on a similar process. And so there was a video last week that talked about it, but you just want to remember that like interacts with like. And so if we have a polar compound and we have a nonpolar substance, then our nonpolar substance is going to migrate up, and those particles are going to be attracted to the stationary phase, right, or the piece of paper. Now, ideally, our liquid should be kind of like a mixture of both, so it kind of attracts polar things and kind of attracts nonpolar things. And so that way, everyone gets attracted to the liquid as it moves up. And what's going to change things is that if you really don't like polar materials, so let's say you're very non-polar, you're not going to feel any attraction to the paper. You're just going to follow the liquid. If you're very polar, then you'll feel a lot of attraction to the paper, and so you won't move as far over that same amount of time. And so we can track how things are attracted to that liquid or not to see how polar or non-polar they are, and then we can use that to identify what materials are present, or in some cases to separate out a solution or a mixture of materials. This works on that concept of like the immiscible liquids, so the ones where they don't like to mix. So oil and water is the most common example. But the reason why is always comes back to like interacts with like, or like dissolves like. If you're polar, you need a polar solvent in order to dissolve you, or you're only going to interact with other polar compounds. Non-polars interact with non-polars. This next part is we're going to talk about some physical traits that are tied in with your intermolecular forces. One of them is surface tension. And so surface tension is a property of a liquid, and it's for them to kind of keep their surface. Now, for our liquids, what this looks like is if you go up into outer space where there's zero gravity, liquids form drops that are spheres. They stay all connected together because they are going to try to maximize the intermolecular forces. What that means is they want less surface area because those molecules on the outside, they aren't completely surrounded by those other molecules, and so they don't feel as many intermolecular forces as if they were in the middle. If you imagine, if this is a molecule here, if we were to build those blocks around it, if it's at the surface, it would only feel these other 5 molecules that can fit. And this whole part up here is exposed to nothing. If we put it in the middle, then we could fit 8 molecules around it, and it would feel even more attractive forces. And so that's the difference, or that's the basis of surface tension, is that the stronger the intermolecular forces are, then the more those things will hold together. The more that tension or that surface wants to stay connected. Now, surface tension is a very interesting thing. Water has a very high surface tension because it has really strong intermolecular forces. So if you want to try this, what you can do is you can take a paper clip and you can float it in a cup of water. That paper clip is going to sit there at the very top of your surface. If it doesn't, what you can do is try to spread it out to get even more surface area for the paper clip. So you can unfold it a little bit. Or if you want it to sink, you can go ahead and squeeze it together. And you'll see that your surface tension, this attraction between the water molecules, differs, or sorry, the attraction between the water molecules is able to support that weight of that paper clip because they want so badly to stay in that same form as where they are. They want to stay cohesive, all connected together. It takes a bigger force in order for them to finally overcome that surface tension, and then finally it will break that tension, and then it will sink. I'm going to link a little demonstration that you can do at home if you want, where you can practice with the paper clip, and you can see some interesting results. So surface tension all comes down to this idea that because they have fewer neighbors to attract them, the surface molecules are less stable than those in the interior. So surface tension exists because they are trying to hold that exterior and hold them in towards the rest of the liquid. It's why if you put a drop of water onto the surface of a table, the water will keep its drop shape. Right? It will stay connected. It won't just completely go away from each other. So things that impact surface tension, intermolecular forces. The other one is raising the temperature. The higher the temperature, the more the molecules will move around, the less surface tension we will see there. That increased molecular motion makes it easier to stretch the surface and to break them. On that topic, viscosity is a similar concept. Viscosity is your resistance to flow. So things that are very viscous means that they don't flow well. Now, everyone can think of an example of a very viscous liquid. The most common one that I've heard is something like honey or syrup. Both of those are liquids. And when you pour them out, they don't flow very easily, right? If you have syrup on your plate, you can turn that plate to its side and the syrup will flow slowly compared to if you have water on your plate. So water is like a good starting point for viscosity. It's kind of in the middle there. There's materials that flow even easier than that, and then there's ones that flow even harder than that. And so the ones that don't flow very well, it's because they have strong intermolecular forces in there. And so for a lot of the ones, like our honey or our syrup, part of the reason why they don't flow very well is that they have a lot of sugars or compounds inside of them that help increase their intermolecular forces. So as those intermolecular forces increase, then they aren't able to flow as well. Now that's one aspect of it. Viscosity is also impacted by the molecular shape. Now we talked a little bit about that molecular shape. You can kind of think that when we had that long chain, there was more interaction versus when we had those branched ones. So less surface to surface does play a role in our viscosity. It's because it gives us lower attraction. Now, if something looks a lot like a sphere, that's part of the thing that helps us understand that it can roll more easily in some ways, is you can see that a sphere has very little interaction with its other spheres compared to sheets of paper. Right? Sheets of paper don't roll very well because they have a lot of intermolecular forces between them in comparison to a lot of like ball bearings next to each other. Right? And so you can kind of imagine that your molecular shapes impact your viscosity. Now, if you ever need to clean something that has a high viscosity, or let's say that you want to get that last bit of syrup out of the container, one way to do it is raise the temperature of the liquid. When you raise the temperature of the liquid, you're increasing that kinetic energy. It's going to allow things to flow more easy because they can overcome that action or those attractions. So if you want to get that last bit of syrup out, put it into some hot water, flip it upside down, and it will flow down to the cap a lot more easy than if it's fresh out of your refrigerator and it's going to be nice and cold. Right? So that's one way to help overcome viscosity. Now, capillary action is a similar concept. Capillary action is the ability of a liquid to flow up a small tube away from gravity. So if you have a straw and you put a straw into water, it generally stays the same for your water temperature or level inside and outside. But if you make an even thinner straw, we can start to see that things climb up. And so if you do chemistry in the fall or moving forward, what you can see is that if you use something called a capillary tube, it's a tube with a very small opening in it. This is a picture of one, right? These capillary tubes. And so when you stick those in water, you can see that it's drawn that liquid up inside that tube. So capillary action is kind of the result of two forces working together. We have the cohesive ones, so that's the desire of our liquid molecules to stay together. And then we have adhesive ones, where those molecules are attracted to the surface of the tube. So the adhesive surfaces or forces kind of pull the liquid to the side of the tube. And as those forces get pulled to the side, well, the liquid wants to stay together with its cohesive force, and so it starts to pull the interior of the liquid up with it as well. So you can kind of see that the edge of our liquid is going up first, and then the middle is getting dragged along. Now, this will continue depending on the strength of our intermolecular force until finally gravity is enough to prevent us from moving up. There's enough gravity pulling down on this liquid in the middle to prevent it from climbing any farther. Now, the narrower the tube diameter, the higher the liquid that can come up because the less liquid needs to move up there. So a straw has got too large of a diameter. But if you go to a smaller diameter, then we can see this more. You can kind of see this on the big scale, and we call it the meniscus. So the meniscus of water has to deal with that attraction between your liquid and the walls of the container. So when we've been looking at your test tube in water or in your burettes, we've always measured from the bottom of the meniscus. And so our meniscus has been what we say is concave as it goes down. And that's because the edge material, that water, is more attracted to the glass than it is to itself. The glass is more polar than itself, and so it feels stronger attractions to the edge of those glass materials. And so it will start to climb its way up. And so that's why it goes like the edges of the water right next to the edge of the test tube goes up. In contrast, when we've been measuring our barometers, when we look at that mercury, mercury always has a meniscus that's going above, convex. The reason why is mercury, its strong metallic bonds prefer to be with itself more than with the glass. And so it goes away from the glass because it's trying to maximize its attraction to itself more than with the glass. And so those are like some physical properties that are related to our intermolecular forces. So what you want to remember about them is how do they trend with your intermolecular force. So if we have strong intermolecular forces, we should have higher capillary action. We have higher viscosity. If our container is polar and we have a strong polar molecule, then we're going to see a concave meniscus. If we see a convex one, then we know that they are not, that it's more interested in spending its intermolecular forces with itself than with its container. The last part of what we're going to talk about is we're going to talk about our solids. Now our solids, there's three things, or there's two parts that we can have for our solids. We can have what we call a crystalline solid, or we can have an amorphous one. Now a crystalline one means that they have a rigid long-range structure. It means that it repeats over and over again. It gives it a very predictable position. Amorphous means that it doesn't have any specific arrangement in this long-range molecular setup. Right? So we're going to focus primarily on the crystalline ones for this next couple minutes because we're going to talk about something called a unit cell. Now a unit cell is the basic repeating structure of a crystalline solid. Now we're not going to do too much with our unit cells for our class. I just want to introduce the topic to you so you are familiar with what it is, but we're not going to make you memorize these unit cells. We're not going to solve things about the unit cells, but I do want you to know what they are. So our unit cells take on these basic shapes, and it has to deal with where our atoms are going to be located. You can have what we call a cubic structure, where each part of that cube has an atom attached to it. Or we can have it stretched out as a tetragonal, so kind of more like a rectangular shape. You can have it as a rhombohedral where it's shifted. And so we can have a variety of these different crystal shapes. And what you'll notice with these is that their solids of their large scale will start to mirror their small scale. So things that are salt have one type of packing, things that are quartz or marble have another. And it's part of the reason why our gemstones get their different shapes. Or if you look at minerals, why the minerals get their shapes is it comes all the way back down to these atoms and how they're packed together. Now inside that cubic structure, there's three types of cubic packing. We can have a simple cubic where we basically put one atom on each of those vertices. We can have a bodied centered one where we put one atom at each of those vertices and we try to sneak one atom right there into the middle, into the body. Or we can have a face one where we're going to put one atom on the face of each side of that molecule to kind of fill in those gaps. So these different packing arrangements, it all comes down to your intermolecular forces and your sizes and radiuses of your different molecules and atoms present. So big atoms have a different type of packing compared to small ones. compared to when you have a small atom with or a small cation with a small anion. All of those give us different packings, or on the edge of things. And so this is how we would figure out our different packings. So when we compare them, our simple cubic, it has 8 atoms, and each one is giving us 1/8 of it, so a total of 1. Our body-centered one is 8 atoms because it's got 8 corners plus 1 in the middle, so it gives us a total of 2. And then our face-centered one is where we finally start to see the halves, is it's got the 8 in the corner, so each one shares an 8, and then it's got half of 6 ones on each of the faces, and so that gives us a packing of 2 as well. Now, we can tie that in with the radius and the size of the unit cell, and then we can figure out how the densities, but we won't worry about that for this semester, all right? Instead, we do want to get an idea about how to measure our different ones. So corners are eighths, edges are quarters, and then these ones that are in the middle, the faces, are half. And so in this case, if we want to think about how many different options we have, we want to think about, well, our gray ones are going to be our sodium, and we know that because they're smaller in their size. And so our sodiums are 1, 2, 3, 4. So we have 4 on an edge, 5, 6, 7, 8, 9. We should have 1 more in that back edge, 10. We should have 1 more down here, 11. We should have 1 more in that back edge, 12. Okay. So if we imagine that each one of those edges fits that quarter of that NaCl, and if we have 12 of them, then we should have 12 times 1/4, which is going to be 3. And then the last part is there's going to be 1 right there in the middle because it is a body-centered. Or sorry, it is face-centered. And so if we look at our face-centered, we should have 1 right there in the middle. And so you can see now the total number of our sodium ones is 1 plus 12 times 4, or 12 times 1/4, which is our 4. On the other side, our chlorine, we have 1, 2, 3, 4, 5, 6, 7, 8 edges. Sorry, not edges, 8 corners. We have 1, 2, 3, 4, 5, 6. So each of the faces of cubes, right? So there's 6 cubes, so we should have 6 faces. Oh, sorry, there's 1 cube, there's 6 faces, so we should have 6 faces. We should have 6 of those chlorines on each, from each face. And so we should get to a total of 8 times 1/8, so that's 1 plus 6 times 1/2. That's going to be 3, so we get a total of 4. So each of those unit cells is packed with 4 sodium ions and 4 chlorine ones, which kind of makes sense because our empirical formula should be our NaCl. Now this one is going to be extra, so you don't have to worry about it. This is going to be how you would find your density. But what it tells you is basically that if we have an edge length, we can find the density of it from grams per centimeters, because we can go back and we can look at this radius and we can find the edge of the cube. We know how many atoms there are from our packing, and so then we can anticipate what size it is. So if you want to see what that looks like, you can do that on the next couple of slides. It's not going to be something that you have to do for your exams, but it is something that you will get back into in the future. So it's something to think about. The bigger part that I want you to make sure that you know and practice is how you identify your non-molecular solids. There are different types based on the melting points and the boiling points. So our non-molecular solids are basically solids that are going to be held together by different types of forces. So sometimes what that is it's going to be things like our lattice or ionic solids. So what's going on here is instead of our molecules being attached, this is our salts, so those ions holding it together. So this happens between our ionic compounds and we can remember that we have an ionic compound because we should have a nonmetal and a metal. So all of these non-molecular solids that we're going to see, we're going to show that they have these kind of larger structures that taken on, and they all end up having really high melting points compared to our molecular ones. Because what's holding these non-molecular solids together is going to be stronger forces. They're not going to be held together just by London forces or dipole-dipoles. They're going to be held together by things like ionic forces or covalent bonds. And so they're going to have much higher melting points. Or they'll be held together by metallic bonds. So instead of us breaking those weak intermolecular forces, we have to break those stronger covalent bonds, those ionic bonds, things like that. So the ionic version of it is going to be our lattice structure or our crystal lattice. Network solids are going to be when we have these covalent substances held together. So you know that something is going to be a network solid because it's going to be nonmetals only. And then it should have a really high boiling point. So imagine that 100 degrees is your water. Now water is a molecule and it's got a pretty high melting point or boiling point. So if you're in that 100-degree range, you could still be a molecule. But if you're in that several hundred degrees range, let's say you have 500 degrees or 1,000 degrees, now you're not really going to be held together by intermolecular forces. You're much more likely to be held together by things like covalent bonds. And so that's one of the trickier ones to identify because it could be either a molecule or it could be a non-molecular solid. And so you want to look at your boiling point and use that to give you some ideas. Of course, there's a solid for our metals as well. That's our last type of bond. And so that would be our metallic bonds. So they have a high boiling point and melting point because like our ionic bonds or our covalent bonds, they're going to be held together by those strong attractions between each of their, between their sea of electrons and each of those metal nuclei. So it kind of breaks down to this, that when we see our solids, we should be able to separate them between our molecular solids or our non-molecular ones. And so what you want to look for is the type of bond that's present. These are ionic, these are metallic, and then the only part that we have to separate is that both of these are covalent bonds. So this is going to be our low boiling points or melting points. And these are going to be our high boiling points or melting points. So let's try that. Let's go ahead and classify these as being either molecular, ionic, network, or metallic solids. And we should be able to go through and we should do that. Zirconium is a metal, so that's going to be a metallic one. Lead is also a metal, so that's also going to be metallic. Calcium nitride, that's a metal and a non-metal, so that's going to be ionic. Graphite, well, that's all non-metals. And so let's look at its boiling point. Well, that's a really high boiling point. So that means that it's probably a network solid because it's going to be held together by those covalent bonds. Phosphorus, on the other hand, that's also going to be covalent because it's all nonmetals. But 44 degrees, that seems pretty low for its boiling point, or sorry, for its melting point. And so we can consider that to be a molecular one. And so that's kind of how you can go through and identify this. Now, this takes some practice. And so I'm going to upload a worksheet so that way you can practice them and classifying them as the different types. You can also identify inside of your molecular solids, well, what is the strongest intermolecular force there? Is it hydrogen bonds? Is it dipole-dipole? Is it London forces? So that way you can practice kind of all of your intermolecular forces at once. Now, these next section is kind of some sample practice problems for what that looks like for our intermolecular forces. And so you want to walk through them, and then the answers are on that next page. So things to pay attention for is think about your intermolecular forces. How do you get their different strengths? In this case here, I'm giving you the values in dBs, So think about what that means. If this is our dipole moment and the strength of that dipole, think about how that relates to our different points. We should be able to anticipate which one of these should have our highest bonding point or our lowest one. So think about the types of bonding or intermolecular forces there. So you can think about their bonding, their forces between them. Same thing in here. In here, you want to think about what types of intermolecular forces do you have present. And so this time I've drawn out the structure for you. And so you want to think about what's different. Now, all of these have the same amount of hydrogens and carbons and oxygens. So you want to think about what might be separating those from one another. So that will be it for today. We'll do a little bit of practice problems on this. But the other thing that I wanted to talk about, just so that way you can be aware, is there's one additional topic. It's called X-ray diffraction. X-ray diffraction is it's a very interesting concept, but it's a little bit we're not going to, kind of like our crystal packing, it's not going to be something that we're going to cover in our class, but I'm going to link it into the lecture because I think that in some cases can be really interesting. Right? So this is how you can study crystals and you can identify materials. And what happens is that when an X-ray gets shined onto a sample, when it's a crystal, some of that light will come in and get bounced back from the surface, but some of it will be able to penetrate to that next level and get bounced back. And we're going to see a difference in that angle because it's had to go in deeper. That extra distance before it gets reflected back, we can measure that. And that's how we can come up with these different distances. We can figure out how far apart the atoms are separated. And we can solve for what we call the Bragg equation here, where we can look at the different spacing between the planes, and it gives us an idea about how thin or how large the crystals are. Okay. I find it as a very fascinating field overall. It's a little bit too much for what where we are in the class, so we're not going to cover it this semester. But it is something that I think is really interesting. So I'm going to make a video that's talking about that inside of your lecture. The other part I want to point you out to is we do have exam 4 coming up. And so this is going to be an ACS-based one. I am not quite sure exactly how many questions are going to be on there, but it is going to be a little bit faster. And so starting next week, we're going to be practicing some of these ACS-style questions. And so you want to make sure that you're spending a little bit of time working on that. You do want to start reviewing for them. Now remember that for exam number 4, it's cumulative. So you want to start with that short practice test that's inside the ACS review book, or you want to start to pull out some of those practice problems from each of those chapters that we've done. Well, by the end of the class, we'll have done a total of 12. So that way you can kind of practice and see what you still know and what you don't. Okay? So you want to start working through some of those now so that way you can build a study guide. And then that's going to help you as you try to build a note card for the final exam. Okay, good luck.